Hello everyone, my name is Daksh Mehta and I am a student at Bennett University. Today I am going to be explaining about closure properties of context-free languages. So let's get started. So the first question that arises in our mind is, what are context-free languages? So context-free languages can be thought of as an extension to the regular languages which we've already studied, and they can be considered as a higher level language than regular languages. As we know that regular languages were accepted by finite automata, so in this case, context-free languages are accepted by push-down automata. And we know that every language has a grammar. So as the regular language had regular grammar, here context-free languages are described using the context-free grammar, which is the generator of this language. So, a context-free grammar is a simple recursive method of specifying grammar rules or production rules which can generate strings in a language. These languages are known as the CFLs. The language generated by the context-free grammar is what is called as context-free language. So, let's take a look at what we mean by context-free grammar. So, context-free grammar can be defined using four tuples as G. Here is our grammar, which can be defined as V, T, S and P, where V is the set of variables of non-terminal symbols. What we mean by non-terminal symbols is that uh, all the symbols which are capital or uppercase in nature, such as S, capital A, capital B, S1, all the capital letters are known as non-terminal symbols. T is the set of terminal symbols, which can be small a, lowercase b, small b, c, and so on, 0, 1, etc. S is the start symbol from which the production rules start, from which our grammar starts. It can be denoted with some other letter also, but as convention we use it S only. So S is the start symbol. P are the production rules. What production rules mean is that they define the grammar and the grammar in turn defines the language. So the difference between regular grammar and context-free grammar is this production rules only. So as we're studying about closure properties, it would be better if we know what do we actually mean when we say that a set is closed under an operation or it is not closed. So we say that a set is closed under an operation if performing that operation on members of the set always produces a member of that set. I'll repeat this line again. A set is closed under an operation if performing that operation on members of the set always produces a member of that set. So if this is not clear, it would be clear once we understand this example. Suppose we are given two context-free languages, which are L1 and L2, and we perform an operation on these languages which is denoted by X. X is just an arbitrary operator which we've used to explain this example. So L1x L2, L1x L2 would give us L3, where L3 would also be a context-free language. So as we can see that we performed an operation on two context-free languages and the result is also a context-free language. So we'll say that the context-free language or CFL is closed under this operation X. So now let's take a look at some of the basic properties, some basic closure properties of context-free languages. In this column you can see the name of the property and this column you can see whether it is closed or not. So we say that context-free languages are closed under union, they are closed under concatenation, and they're closed under clean closure. However, context-free languages are not closed under intersection as well as complementation. So in the coming slides, we'll see why they are closed and why they are not closed and examples of them. So first we'll take a look at the union. So L1 and L2 have been given to us already, and these two are two context-free languages. So we say that their union L1 union L2 will also be a context-free language. Let's take an example. Suppose L1 is given as A and Bn where n is greater than 0, the corresponding grammar G1 to L1 would be given by the production rule. S1 goes to AS1B or AB. Here we say AB because n is greater than 0. In the second language L2, which is CMDM, m greater than equal to 0, the corresponding grammar G2 will have the production rules given as S2 goes to CS2B or epsilon. Here epsilon has been given because m can be 0 as well. So if C is 0 and D is 0, essentially our language contains nothing and epsilon represents nothing. So if we take the union of L1 and L2, we will get ANBN union CMDM, which we can see is also a context-free language. So the corresponding change in the grammar, which we'll have to add an additional production, would be S goes to S1 union S2. This symbol right here represents the union. So S goes to S1 S2, S1 union S2 will be added production to the already grammar present, and then below these we will write S1 and S2, which have already been given here. So now let's take a look at concatenation. If L1 and L2 are context-free languages, then L1 L2, their concatenation would also be context-free. So here is an example. L1 is ANBN, n greater than 0. L2 is CMDM, m greater than equal to 0. These two languages are the same as in the previous example. Here we can see ANBN, CMDM, m greater than equal to 0, n greater than 0, and their corresponding grammars is this. So I have not written the grammar here. So the concatenation of languages L1 and L2 would be L equal to L1.L2, which will be ANBN CMDM, which we can see is also we can say this is also a context-free language, and the corresponding grammar will have the additional production. We will add one more production to the grammar which already exists, which will be starting symbol would be this now. S goes to S1 S2, and below that we will write S1 as this and S2 as this. So that was concatenation. So now let's move on to clean closure. So clean closure is also known as clean star. The clean star is a unary operator on a set of symbols or strings that gives the infinite set of all possible strings of all possible lengths over sigma, including lambda. Sorry, over epsilon, including lambda. Lambda is the same as epsilon. I'll repeat this. The clean star is a unary operator on a set of symbols or strings that gives all the infinite set of all possible strings of all possible lengths over sigma, including lambda. If the same language can be reproduced multiple times, the language is said to be closed under clean closure. So for example, if we've given a clean star of a, it can be 0 times a, which is epsilon, single a, double a, triple a, and 4 times a, and so on. It can go on and on. So let's look here at an example I've written. L1 star means L1 is a language which L1 star here is the clean closure, and this language is given by the corresponding grammar G1, and G1 produces S1. Here is the production. S goes to S1S or lambda. So for 0 times, if we don't want S1 to come even once, we'll simply go S tends to lambda, which is here. So we get lambda. For only one time, we'll say S tends to S1S, and then S can further go to lambda. So we parse it top to bottom, left to right. We'll see S1 lambda, which will further give S1. If we take it 2 times, we'll say S1S, S will further go to S1S, and then S will further go to lambda. We parse it top to bottom, left to right, S1, S1, lambda, which will give us S1 and S1. And this can go on and on for 3, 4, any number of times. So here is an example of clean closure. Languages A and Bn n greater than equal to 0. Corresponding grammar will be S tends to A capital AB or epsilon. So the clean star would be A and Bn. So the only change in the grammar which we'll have to make is we'll add an additional production, which will be S1 goes to SS1 or epsilon. So now we come to intersection. We already know that intersection is not closed. So if L1 and L2 are context free, then their intersection may not necessarily be context free. So to prove whether an operator is closed or not closed, we just need to prove that it is not closed, we just need to find a single example that disproves it. So here is one such example. L1 is A and B and CM, n greater than equal to 0, m greater than equal to 0. L2 is AM, B and CN, n greater than equal to 0, m greater than equal to 0. L equal to L1 intersection L2. The intersection of these two languages would be AN, B and CN, where n is greater than equal to 0, which is a context sensitive language and not a CFL, because here we have to make two comparisons two comparisons instead of just one. So we'll say that CFL is not closed under intersection. So now the final property is complementation. We are given L1 and L2, which are context-free languages. So let us first assume that CFL is closed under complement. Although we already know that it is not closed, but here we'll prove it by contradiction. So let us assume that CFL is closed under complement. We take the intersection of the two languages, L1 intersection L2, which can also be written as L1 complement union L2 complement whole complement, which is the De Morgan's law. And this will also be a context-free language as it is closed under union. So L1 union L2 whole complement is also CFL, as we have assumed that context-free language is closed under complement. So its complement will also be a context-free language according to the assumption made by us. So L3 complement would also be a CFL because of the assumption made by us. L3 complement is a CFL, and if we take the complement of this, which would be L3, it is also a CFL because we've assumed that it is closed under complement. So now we see here that a contradiction arises, that L1 intersection L2, which is L3, is coming out to be a CFL. However, we already know that L1 intersection L2 is not a CFL because CFLs are not closed under intersection. So by contradiction, we can say that CFL is not closed under complementation. So that was it from my side for today. Thank you for watching, and I hope I was able to explain these concepts to you well. Thank you.